Question 6 asks us to use induction to prove this result. So again, for induction there's a few steps that we need to follow, and we must start with let Pn be the statement, and we write down what we have. That the sum from r equals 2 to n of r squared plus r plus 1 times r factorial is equal to n plus 1 squared times n factorial minus 4. Now, this is true. We want this to be true for all n that are positive integers, but if you'll notice, it makes no sense if I set n equals to 1. So I should also say that n has to be greater than or equal to 2. And this has certain implications. Why? Because it means my base case isn't n equals to 1. The lowest possible number I can put in is n equals to 2. So I start when n equals to 2, and this is now my base case. So what is the left-hand side of P2? So the left-hand side would be the sum to 2 from r equals to 2, r squared plus r plus 1, r factorial, and that would be just substitute in r equals to 2. 2 squared plus 2 plus 1 times 2. And that in this case is 4 plus 2 is 6 plus 1 is 7 times 2 is 14. Right. What about the right hand side? The right hand side of P2 would be, again, just substitute 2 into this one, 2 plus 1 squared times 2 factorial minus 4. So 2 plus 1 squared, that's 3. 3 squared is 9 times 2 is 18 minus 4 is 14. So since the left hand side is the right hand side, we can therefore conclude that P2 is true. What next? Next I have to set up my induction hypothesis. So this is where I assume pk is true for some k. And again, it's important that it's some, not all. I also like to write out what this means. This would mean that the sum from r equals 2 to k of r squared plus r plus 1 times r factorial is equal to k plus 1 squared k factorial minus 4. So usually write i.e. first. So i.e. that this is true. Now I want to prove, or want to show, pk plus 1 is true. Why? Because it's like the domino effect. If P2 is true and pk implies pk plus 1, then since P2 is true, that means P3 must be true, and therefore since P3 is true, P4 must be true, and since P4 is true, P5 must be true, and then 5 means 6, 6 means 7, 8, 9, so on and so forth. So if I can prove that pk implies pk plus 1, and I know P2 is true, that means it's going to be true for everything bigger than or equal to 2. They will all drop over like dominoes. So I want to show pk plus 1 is true. How do I do this? I start with the left-hand side of pk plus 1. So what's that going to be? That's going to be the sum to k plus 1 from r equals to 2 of r squared plus r plus 1 times r factorial. Now, one thing that I really need to do is make use of my induction hypothesis somehow. So I'm going to take out the k plus 1th term from this and just add it on separately at the end. So like this. Then plus the k plus 1th term, so where r equals to k plus 1. And that gives me k plus 1 squared plus k plus 1 plus 1 times k plus 1 factorial. Bravo! Now I can apply my induction hypothesis to this part in here. So this is, by my hypothesis, k plus 1 squared times k factorial minus 4. And then I still have plus this whole mess in here, which I'm going to simplify a little bit. That's going to be k squared plus 2k plus 1 plus k plus 1 plus 1. K plus 1 factorial. Okay, does that help me at all? Yes and no. What have I got in common? Well, I've actually got k factorial in common with both. In fact, I've got more than k factorial in common. Are you guys okay that I can write this term here as k plus 1 times k plus 1 factorial? Right? Minus 4. And then plus, sorry, that 4 wasn't quite right. This is k squared plus 3k plus 3 times k plus 1 factorial. So I've got k plus 1 factorial in common to both, but not this 4 in here. But that's okay, because I want a minus 4 out the back, so that can just live out the back. That's perfectly okay with me. So k plus 1 factorial. Then from this first one, I have k plus 1. Leave the minus 4 at the back. Then plus k squared plus 3k plus 3 minus 4. So this is k plus 1 factorial. Then if you look at this, this is now k squared plus 4k plus 4 minus 4. This is k plus 1 factorial k plus 2 squared minus 4. And that is the right-hand side of pk plus 1. So now I've proven that pk, as long as pk is true, and sorry, I made a mistake, I should have written by hypothesis here. So since I've proven that pk implies pk plus 1, I'm actually done with this part of the proof. So what's left, the only thing that's left to do is to conclude. Therefore, P1 is true and PK true implies PK plus 1 is true. Therefore, by the process of mathematical induction, Pn, sorry, this is not P1 either, this is P2. Pn is true for all positive integers n that are bigger than or equal to 2. And we are done.